So welcome everybody to our 34th Inspiration Exchange session, and thank you so much for joining us today. Super excited about today's session, which is our first in Inspiration Exchange about large language models. To give a very brief overview of today's session, we're going to start, as usual, with a couple of presentations from various students in our group. The first presentation is going to be on the use of large language models for unbounded code generation, and it's going to be given by PhD students Sam and Max from our lab. And then we're going to speak about large language models for Bayesian optimization with Tennison and Nicolás. In the second half of our session, we're then going to move to a roundtable and Q&A. And I'm delighted to welcome Professor Guillermo Sapiro and Dr Hoifung Poon for this session, and I'll introduce them more formally later in the session. If you have any questions for any of our speakers at any point, or our panelists, please put them in the Inspiration Exchange channel on Slack, and we'll post a joining link in the chat now for this. And please do ask questions as early as possible when you have them, and we'll try and take as many as we can at the end of the session. Without any further ado, I'd like to kick off this session by inviting Professor Mihaela Schaar to give a brief discussion of her vision for large language models. Mihaela, over to you.
Thank you very much, Fergus. Hi, everyone. I'm really very excited about this session today about large language models. And in the past year, we have seen some amazing advances using large language models for a variety of natural language processing tasks, from question answering to code pilots to code generation and many, many other wonderful examples. And these are all very important problems. And indeed, the first talk on this Inspiration Exchange and one talk in the next one are going to discuss advances made by our own lab in these very important areas. However, I'm even more excited possibly about how we can use large language models to advance the reality-centric AI agenda that our lab has put forward at the beginning of last year. And in this, I'm really proud to say that our lab has taken what I believe to be really the first steps in bringing the machine learning community to consider the use of large language models to empower and enhance this reality-centric agenda. For instance, today in the second presentation, you are going to see how we can use large language models to empower large-scale machine learning and complex tasks in optimization, with an example in Bayesian optimization, but transcending Bayesian optimization. And this has numerous real-world applications, from AutoML, an area that we are very passionate about, to neural architecture search, to many others. I'm also very excited about how large language model can be used to make machine learning less brittle. As you know, in the reality-centric agenda, we talked a lot about, despite the fact that we have machine learning that is very powerful, machine learning remains brittle when we are applying to complex real world. So what I'm also excited about is how we can capitalize on the power of large language models to make machine learning more robust, more trustworthy, more available to use to anyone, inclusively people who may not know how to code or may not have enough data to do machine learning, and how we can do that in a safe, trustworthy, and human empowering way. So this brings me to finally, and possibly what I find even more exciting, and we have started to show this just very recently, and this is how machine learning can really bring, how large language models can provide machine learning with the ability to transfer very powerful human thoughts into machine learning thoughts, into the world of machine learning, and thereby teaching machines some of our own thinking that can augment and transcend just the use of data, thereby being able to bring important concepts such as meta-learning to new levels, And vice versa, how we can use large language models to translate machine know-how into understandable human intelligence that can empower humans. So I think this is a new and exciting era for machine learning in the era of large language models. And I hope that we, the community that comes together in these inspiration exchange sessions, are going to think creatively about how we can use large language models to advance the reality-centric AI agenda and empower humanity rather than replace or destroy it, and make progress in important fields such as medicine, education, climate change. And with this in mind, this is why I'm feeling extremely thankful to the two panelists today, Guillermo and Hoifung, because they are very good representatives of how they use this new technology in a human empowering way. So thank you, and I hope you all get inspired and we use large language models and beyond for improving this important agenda. Thank you, Fergus.
Yep. Hi, everyone. I'm Sam. This is L2MAC, Large Language Model Automatic Computer for Extensive Code Generation. This is a joint work by excellent co-author Max and my supervisor, Mihaela. And I'll give the floor to Max.
Thank you for the introduction. So, off-the-shelf LLMs have some flaws. So, for instance, as you can see here, they cannot simultaneously execute long-term plan and its sub-steps. And it cannot cope with huge environments. And that seems like it's because of a limited context window, but it's more fundamental because if we increase the context window, the attention gets degraded. They also have another problem, which is that they cannot ensure correctness of their output. And that's like hallucinations and because of their stochastic nature. But at the same time, they have a lot of good properties. So for instance, they are very good at small generation tasks if you provide a good enough context window. They are good at splitting a big task into its subtasks, and they are also able to reason about the function of an element and provide tests that guarantee it. Finally, they are also good at considering the feedback from an output and iterating on it. So the thing is, how can we propose a system that embeds an LLM and exploits this latent potential without falling into its flaws? In this case, we focus on code generation tasks because of their importance, and also because in the setting of long code generation tasks, these flaws become evident, and the larger system can help overcome them. So when one thinks about this task, it is clear that we need a memory, just even to store the output that we're aiming for. The problem is that current approaches for memory are either very simplistic in the writing mechanism, which consists essentially of appending their output to the previous memory, or they are very restrictive, such as having memory in the form of dictionaries and databases, which is not flexible enough for most cases. They completely ignore validation of the syntactic and the semantic validity of what they are outputting, and also they do not address the problem of this long goal and short goal management. So in this presentation, we cope with, or we address how we can do long generation tasks, and in particular, how we can do long code generation tasks through L2MAC. So I give the place back to Sam.
Amazing. Thank you, Max, for introducing. So now we'll look at the large language model automatic computer, or what we call L2MAC framework. So this is the first practical LLM-based stored program automatic computer for long and consistent output generation, generating an output which is vastly greater than the context window constraint. How it does this, it has an external memory, which has two components. We have an instruction registry, which is populated with a prompt program to solve the user-specified given task in a file store, and which will contain the final and intermediate outputs. And each instruction is executed by a separate LLM instance whose context is managed by a control unit capable of precise memory reading and writing to ensure effective interaction with the file store. So this has immediate benefits for tasks such as extensive code-based generation, of it can generate extensive code structures bypassing the constraints of finite context window, can produce code that fulfills complex user-specified requirements, can automatically correct generated code that has syntactic or functional errors, and can correctly condition on and integrate the existing code base as we generate code. So let's look at how exactly this works. So a user will come for generating a large code-based application. They may want to generate, say, code for an online chat application platform. And this may have many features such as sign up, profile settings, many different user pages and different modules behind the scenes. So we look at large-scale system design code generation tasks. Now, our LLM will generate a prompt program, which is a series of sequential instructions, and then it will take each instruction into a separate new LLM coder agent instance, which will then code up the code specified to meet this particular instruction, whilst maintaining this external file store memory between independent instructions. So as you can see here, we have an LLM coder agent that writes 3 individual files to start with. Now we actually specify when it generates code to help generate consistent memory to generate also tests as well when it generates functional implementations of the code. So what's important is these tests, in each code piece is generated, will be run and have to pass for the code to be complete, and then that task to be complete. And in this case, it has completed by writing 3 files out for this initial designing the application structure and including a mock database and implement user registration and profile management modules. And then this also summarizes the actual what has been achieved in this instruction step. This summarization is then fed into the next instruction set, which is taken from the initial prompt program, if you will, and the next feature or implementation to implement, in this case, is to implement user registration with sign-up and password recovery endpoints. Now, we have to condition the new code files on the existing code files that have been generated within the existing code base. So here we have an app, database, and also tests as well. Now, the LLM can actually precisely read and write files from this external memory store that it's built up. So in this case, it's actually specified to read files within the external memory that it has, to read this within context, and then it can then write new files. Here, it can override existing files and also create entirely new files. What's interesting here is when we create new functionality, we may break existing functionality done in previous steps, as we see here. So it's failed some unit tests that is previously written previously. So therefore, we can iterate with the LLM the errors of these unit tests to correct the errors, and then actually correct to make sure the code is fully working before moving on to the next instruction step. And we iteratively repeat this many instruction steps until we complete a complete code-based generation that solves the very detailed user-specified requirement tasks. And overall, this framework, we call it Code L2MAC. So how does this work? So we operate by having this prompt program of instructions, and we take one individual instruction and we give it to the LLM, in this case, our processor. And what's really key is we have precise read and write and evaluate tools for the external memory. So therefore, we can read and write files, and then we can check whether this instruction step is being completed. If it has, we can then test the code for static errors. So we use static code error analysis. If any errors are detected, it's iterated to fix these because they need to be fixed before subsequent iteration steps proceed. And also we run all the unit tests that have been generated alongside generating the code for each module. And these have to pass as well. We also have some corner cases, which you can read more about in the paper, of how we handle cases where we actually extend the context and we have to iterate the same instruction for future iterations, and also how we can summarize the output as well. But overall, this builds up a very large code-based structure in the external memory, and really code checks are key to correcting generated code that has syntactic static errors and functional errors, meaning unit tests fail whilst conditioning on and integrating with large code-based files. So we can look at existing approaches in the literature. So we see reflecting LLMs, or most famously, autonomous agent LLMs with memory, such as AutoGPT. Now we can correctly handle context for a very large, long task, and we can actually correctly precise read and write to the external memory and check the generated output. So how do we perform? So what's amazingly, we perform state-of-the-art performance on large code-based generation tasks. So here we list the percentage of functional features specified that are fully implemented in the number of, and also the number of syntactical errors that's achieved with each method, and the number of lines of code, and the number of self-generated tests that pass. Now we can see CodeL2Mac fully implements the highest feature percent of user-specified feature requirements across all these 3 tasks. So generating an entire application of URL shortener application, an online social media application, and also an online chat application. And it achieves this by achieving minimal syntactical errors. So here, 0 syntactical errors, whilst also writing a large number of self-generated unit tests. Therefore, CodeL2Mac is state-of-the-art for completing large code-based generation tasks, such as large system-designed code generation tasks. So now we go into some of the insights of how CodeL2Mac can correctly perform this by managing the context correctly between each individual instruction step. So we observe actually CodeL2Mac through creating this initial prompt program, saving this to internal external memory, and then loading each instruction in sequentially into a new separate LLM instance, can actually retain a high number of user-specified feature requirements within the instructions and perform instruction-oriented, almost managing this long-term plan over many long-running iteration tasks. And we see we can actually retain the highest percentage feature requirements within the instructions in the beginning throughout the generation of completing an episode, whereas competing methods like AutoGPT actually summarize it into 5 instruction steps, and it's very lossy. We also look at, can it actually precisely read and write existing files that's generated and update these over time? And we answer the question of yes, it can. So it has an understanding of existing code files that are generated, allows it to update existing code files, especially these generated many instruction steps before. It can view the files when it's not sure what's in these files and actually update them. So we see here, red dot means it's created a file, and then blue dot means it's read the file. And we can see here in AutoGPT in the bottom, AutoGPT creates files and then often doesn't read what it's created, leading to errors as it propagates over time. Whereas CodeL2Mac can actually correctly generate files, read them, and then actually overwrite them or update parts of these files, which is really key when implementing more features for existing code bases it generates and grows. Now, what this naturally leads to is actually methods like AutoGPT, because it forgets what files is written, errors propagate and accumulate over time. Whereas actually what's really unique with CodeL2Mac, we have this static checking and functional checking of the code, which allows, obviously we know LLMs are stochastic, so the LLM output stochastic can contain errors. And when errors are generated, they can be detected and promptly fixed by iterated with the LLM instance until we have a working, essentially 0 error implementation of the external memory of the code base. And we can iterate this over, whereas existing methods accumulate errors. So our contributions are, we're the first LLM-based stored program computer framework for long output generation tasks. We provide a practical implementation for code generation tasks called CodeL2Mac, which uses code checks to correct the generated code that has syntactic and functional errors within, whilst conditioning on and integrating with the existing code base. Empirically, CodeL2Mac can generate large code bases to solve for the first time high-level system design tasks for creating entire applications and observe that it is state-of-the-art. This enables now a practical tool for large code-based generation and to eventually to execute long-running, large unbounded output tasks with an LLM, potentially as an AI assistant. I'd encourage you to check out more of the paper, and we're excited to share the code soon. Thank you.
Okay, so thanks everyone for coming to listen to our presentation today. Today we'll be talking about our work titled Large Language Models to Enhance Bayesian Optimization. And this work was conducted by Nicolás and myself, as well as Nabil and supervised by Mihaela. So before we jump into the method, just to provide a very brief background on Bayesian optimization. So Bayesian optimization is a model-based framework to optimize complex, expensive to evaluate black box functions. So some of the characteristics of these problems are, because of their expensive evaluations, we want to perform as few evaluations or queries as possible to perform the optimization. We also generally assume that these are black box functions, so there's no access to gradient information. And often whatever objective values that we can observe of the function might be noisy as well. So to address this class of problems, Bayesian optimization is a framework that iteratively refines its search space based on some form of prior knowledge that guides it to efficiently search and find optimal solutions. Specifically, model-based BO has the following components. The first of which is a surrogate model. And what this does is that it approximates F. And usually there's some sort of prior knowledge that helps with the approximation. And a good example of this is the Gaussian process, where you can encode some sort of prior about how this function looks like. There is also a candidate point sampler that proposes a set of candidate points, which can be evaluated next. And to decide on exactly which point to evaluate, there is an acquisition function. So another perspective on this is BO can be considered a few-shot learning problem. And this is a problem where we know large language models are particularly proficient at. So what are some of the exact strengths of LLMs? They are very efficient few-shot learners. And thanks to their large-scale pre-training, they encode very rich prior knowledge about the problem space. Or at least they can contain very useful prior knowledge. And they have very flexible ability to understand contextual information. Specifically, we can view LLM and context learning as performing some sort of Bayesian inference, where we're trying to infer by marginalizing over some sort of prior knowledge that is contained in the LLM. Okay, so now we move on to an overview of our actual method, and this is a bit dense, but essentially Lambo is a framework that utilizes the strength of LLMs to enhance model-based BO. And we address this through a few key components, which is shown here. And specifically, we consider the use of Lambo for warm starting. And this is about sampling initial points that can be used to initialize the search process. We also consider using it to propose candidate points by conditioning on past observations. And lastly, we consider its use as a surrogate model, which is to estimate the potential of these candidate points, similarly by conditioning on past observations. We focus largely on hyperparameter tuning tasks in this paper, but so some of the details we'll give will necessarily be related to hyperparameter optimization. Cool. So how Lambo actually performs all these components that we've just described is through the use of structured prompts. And without going into the details about how these prompts are constructed, they sort of contain the following key components. And the first is some sort of contextual description of the actual problem. So this can contain information about the input space, the output space, and the objective function that's being optimized. There's also an optimization history, which is just the points that have been evaluated and their objective values, and these are provided as few-shot examples. And lastly, there are task instructions. So these provide instructions on what a specific inference is to be performed and guidelines on how the responses should be provided. Cool. So we'll now be jumping into the first bit, which is warm starting. And warm starting is a mechanism that is used to obtain diverse and high-performing points to initialize search. And hopefully this can lead to more efficient conversions. And here's an example of a prompt that we use. We have sort of more complete examples of this in the actual paper. But the very important thing about warm starting is we want there to be enough diversity, and we want the warm start to actually improve search efficiency. And this is the first aspect that we investigated, and shortly we'll see why that is the case. And some of the key takeaways that we found were that warm starting with our method can improve search performance, and that is what's being shown here. So here, all three of these purple lines are different versions of our warm starting strategy that differs on how much contextual information is provided. And we see that across all cases, warm starting helps. And he actually mentioned that the warm starting points are fed into conventional Bayesian optimizers. And we also found that the points that are sampled through the warm starting procedure contains a much higher level of correlation between in the hyperparameter space. So that is shown here, where the average correlation is significantly higher than random initialization. And this actually is a very good sign because it indicates some sort of generalizable knowledge about correlations in the problem space that can be used to drive search efficiency. And we also wondered how diverse these points are. So that's what's being shown here. And we find that compared to random initialization, our initialization from warm starting initialization strategy actually leads to less diversity in the sampled points. And this is actually somewhat expected because this is a direct consequence of the higher level of correlation between the points sampled. And next, I'll hand over to my co-author, Nicolás.
Well, I'm Nicolás. Now we are going to talk about the candidate sampler, which is basically the module that's sampling promising points, but now considering all the past information. So this is challenging because we now have to put contextual information in form of natural text into a large language model. But thankfully, large language model, as Tennison was saying, is very good at future learning. So we can put all the past observation in context learning. So which is basically the pairs that have the features and the score achieved for each features. And to sample promising candidate points, we can condition on which score we want to achieve. So that is basically S prime, and it's constructed also based on the information that we already have, which is basically the best and the worst score achieved. In this parameterization, we have a hyperparameter alpha that measures the trade-off between exploration and exploitation. So if we're being very conservative, using a score that we already saw in the past, what we are going to achieve is sample hyperparameters that are inside of the distribution of the data. But if we are less conservative and we want to achieve a score that is even better than the ones that are already observed, we are going to find hyperparameters that are outside of the distribution. Okay, so we basically measure the quality of this point using average regret and best regret, which are the metrics using VO literature. And something very interesting is happening here, and is basically an observation that we also made in warm starting, which is basically that our method, because we are considering more information, the variance or the space of the hyperparameters is more constrained than current baselines. And now we move on to the surrogate model, which is basically the module that score how promising are the points obtained from the candidate sampler. So to do this, basically we took a common a common approach using VO literature, which is basically compute the two statistics that are necessary to know if a candidate point is promising or not. One statistic is the mean, which is related to the score, and the other one is the uncertainty. If we are very uncertain about something, it means that it is valuable maybe to measure that part of the space. So calibrated uncertainty estimation is crucial for exploration and exploitation. And we explore this. This is challenging in LLMs because, again, we are using natural language processing and we need to obtain these statistics. So we came with two approaches. One is the Monte Carlo sampling, and we also try other alternatives like varying the ordering of the prompts to reduce the bias produced by the ordering. And so we evaluate surrogate model using common metrics like negatives, mean square error, and regret, and we observe that our method is generally better than the current baselines. Our method, Lambo is a little behind in uncertainty estimation, but it recovers when it catches up when more samples are obtained. So finally, we compare, we evaluate Lambo in an end-to-end manner without including warm starting for fair comparisons. So we evaluate Lambo in an end-to-end public benchmarks like Basemark and HPO Bench, as well as private and synthetic datasets. This was necessary to make sure that the large language model is not memorizing all the information about hyperparameter or about a specific dataset. So we ran this method with 79 total tasks, which is basically all the pairs of dataset and models, and with 5 seats each of them. And you can see that overall, Lambo performs pretty good, and particularly good in the earliest stages of the exploration process. So to summarize, Lambo is a novel framework for Bayesian optimization using large language model. This is one of the first work that demonstrate that LLMs are capable in traditional optimization tasks. And of course, there are many future directions. For example, VO task-like control or experimental design, or even it can be the brain controlling an AutoML exploration process. Here we are limited on time, but in our paper you can find much more details about generative surrogate models, evaluations on prior insights into candidate point proposal, and more benchmarks. So please check our paper if you are interested.
Now I would like to move on to our panel discussion and to welcome our two guests to today's session. So our first guest is Dr. Hoifung Poon, who is a general manager at Microsoft Health Futures. And I'm also delighted to welcome Professor Guillermo Sapiro, who is the health AI lead at Apple and is also the James B. Duke Professor at Duke University. Thank you both so much for joining us here today. Really excited, and I know Mihaela and lots of other people are also very excited to have you here today to speak about large language models and hear a lot of your thoughts on this topic. I'd like to kick off with a very general question towards both of you, just about the roles you think large language models can have in healthcare and biomedicine more generally, where you think these might have the most impact, or maybe already are having impact, and maybe your kind of more general vision in this area.
Thanks so much. Super excited to be here. And thanks, Mihaela and everyone for the invite. Really good to see. I visited you guys in summer 2022, so very good to see some of you. And very nice meeting you, Guillermo. And so I maybe sort of like share some of the kind of like starting from a little bit of our own work, right? So one of our kind of like focus of overarching research is like based on the observation that there has been actually a lot of kind of like increasing amount of real world kind of observational data about a patient, right? So from diagnostics to treatment to outcome, right? Obviously one great source is actually a lot of the kind of like sequencing technology and sensor, right? So Guillermo, you did lots of great work there, right? And the other kind of like amazing source is the digitization of electronic medical records, right? So that actually only happened in the past couple of decades. And with all those kind of real world observational data, that come this really sort of like exciting kind of opportunities. And one way that I tend to think about sort of like the latest sort of like generative AI kind of disruption is that for the first time ever, right, we can start to imagining kind of like learning this kind of really high fidelity patient embedding, right, that can almost serve as a increasingly close to be a digital twin of a patient by essentially learning from all this kind of real world observational data and multimodal, right? Now, given this multimodal patient embedding, we can then enable sort of like really sort of like this what's called a patient like me, originally started from rare disease, but really kind of like a very powerful concept to essentially give when a patient come in, if you can actually see a bunch of kind of very similar patients, then you can start to looking into what actually works, right, for the very similar patients. And you can sort of immediately contributing to improving patient care. But you also, crucially, is that you can also identify what actually doesn't work, right? So for example, in cancer, it's still very hard to treat in late stages, right? So, and we go through traditional chemo that kill every dividing cell to targeted therapy that could be very precise, but could also be easily dodged by cancer mutations. And the latest exciting frontier is immunotherapy by mobilizing the immune system, right? And some of the blockbuster drug like Keytruda, right, that actually really can actually almost like miraculously cure some of the very late stage cancer like melanoma and so forth. Unfortunately, the general response rate is only 30%, right? But there are already millions of people who have taken this kind of checkpoint inhibitor. And now if we can start to understand how are those 70% kind of like non-responder differ from the responders, then we can start to pinpoint like where are the missing targets and treatment. And also more importantly, once the pharmaceutical company figure out some of those new promising kind of like drug and targets, we also have this like very almost like precision patient stratification that can enable, you know, much more kind of like precise trials and so forth. And so that actually to some extent, like I think one of the really exciting future is that imagining learning this kind of biomedical foundation model, right? That not only actually like GPT-4 basically predicting the next token, right? But this kind of foundation model with this kind of multimodal patient embedding, maybe we can actually start to predicting next major medical events, right? Like progressions, treatment response, and so forth. And if we can do it with very high accuracy, right? So approaching higher and higher accuracy, we getting closer and closer to solving, you know, precision health. So I think at a very high level, that's kind of like a really, really exciting future. But obviously there are so many facets in that, but I'll stop here and love to hear Gilmore, what you think and what everybody else thinks.
Thanks. Thanks for that. I really appreciate, because you took in a completely different direction that I'm gonna mention right now, which, you know, the scientific discovery, which is great and something that Microsoft has been leading. I'm gonna share in a second something that is both my personal opinion, but let me just give you a warning. As you know, as he was mentioned, I have an appointment at Apple as well as faculty. Recently, I was honored to be at a meeting with Peter Lee, with Irfan's boss, and he asked me a question also for a panel, and I said, you know, at Apple we never talk about the future, we only talk about the past. So we cannot talk about what's up and coming. So don't take any of my comments about, hey, this is coming. But I think I'm gonna try to address that and then bring a slightly different question back to the team following the two talks, the great talks that we just had. There is something very important for all of us to remember, that, just to put it mildly, a lot of doctors are not very good, and a lot of people don't have access to medicine. And that's something that is very, very difficult for most of us, because we are privileged that we are educated and we live in cities with great clinical presence. It's very hard for us to understand that. But I can give you multiple examples, but it's very important for us to understand that most of the doctors that any person in this panel has seen are on the tail of the distribution. So first, we are on the tail of the distribution on access, really, really. So if there is anything that we are on the top 1%, is on access. So maybe we are not on the top 1% in wealth, but we are in the top 1% on access. And we access also doctors that are on the top %. So when people say, what is the role of LLMs or the role of the internet? We have to remember that, let's just think about the 99% of the population that doesn't have the access. I was last week, and the same meeting that I mentioned with Peter Lee, it was organized by Zach Kohane. And your current LLMs are better than most doctors. Let me just put it very simple. And certainly give more access than what's accessible to most people. And that's something important. It doesn't mean that we don't have to get them better, but it's important to understand that this is not Zach Kohane level, which, by the way, is using LLMs as part of his practice. Even him is using. With that, I think it's very important for us to understand the population. And I can give you multiple examples. The population doesn't understand how to use these tools, how to prompt these tools, and how to take the answer of these tools. So I know how to stupidly prompt GPT-4 or Gemini and get a very bad answer. So I can play not a scientist, but an ordinary person. And then I can prompt it right and get just a perfect answer, just perfect. So we always need to be aware that the general public interacts with these tools very differently than we do. So those are kind of my two messages. One is, let's just try that the LLMs become, the tail of the distribution in their quality, so they become the level of the best doctors in the planet. That should be our goal. But let us not forget that most doctors are not like that and access. That's one, and then that the users do very differently. So having said so, I just want to give two, and everybody can decide to ignore my question, but I want to bring back a question to this team, which is, you ask what's the role of LLMs on health. I'm going to ask what's the role of academia on LLM development today, because Cambridge University is a very rich university, but you don't have $1.5 billion to train your model, which, according to rumors, is how much OpenAI has spent at least training their models. So I think we also have, now wearing my academic hat, we need to think what is our role for machine learning today. So you probably just saw Google, sorry, if I'm just to give a good, Google just released Gemini 1.5 today. I can guarantee that made 90% of the ICLR papers on LLM that were accepted but will only show up in April, they made them obsolete. The performance on all those papers is probably already obsolete. No fault to those papers, but they released today Gemini with over 1 million tokens, sometimes 10 million, half an hour of video. So what is our role in academia to make sure that we are not part of that race, but we make foundational contributions that then Microsoft, Google, Apple can take, and they're so foundational that they will survive the test of time of Gemini 2.0 and GPT-5. And that, I think, is a very important question that we should be asking ourselves in academia. I was provocative on purpose, and I forgot I was going to use your second talk as an example. Probably your team can go tomorrow and from now to the ICLR presentation, say, hey, we use, for our paper, we use the LLM X. Now we use Gemini 1.5, and here the results are even better. For us, the LLM is a black box. You keep doing it better, my result will keep getting better. So that is exactly what we should be doing, and that's an example of foundational things that survive the time, and the same for health. So the examples which really excite me about scientific discovery on health, they should be done in parallel to improving the LLMs. And every time there is a new GPT or a new Gemini, you just change one line in your code and boom, it gets better until one day we cure cancer because LLM will become so good that we cure the cancer. We were almost curing, and that's where I think the exciting work is. We should keep the 1,000 people or however at each company with billions of dollars in computer power, keep improving the LLMs and making our work better by doing that. So it's a collaborative environment. Same way as NVIDIA keeps doing better GPUs and we keep doing better machine learning. thanks to that. So it's a collaborative environment.
Completely agreed, Guillermo. You said it a lot more eloquently than me. This is what I was trying to say at the very beginning, that really I'm excited about large language models beyond just the conventional tasks. And really it is this complementary approach. And to some extent also in the past, we talked about a lot about health. Health is very, very dear to my heart, but other problems in climate, in education, maybe we can use this innovative tools to really help us think differently about a lot of real world problems that in the past were difficult to maybe deal with because we didn't have the know-how, we didn't have access to experts, we didn't have access to data. So now we do have access to a lot more due to large language models. So I'm completely, and thank you very much for this point. I think it's a very, very important one.
Yeah, I think it's fascinating, and I really appreciate this discussion. I have to cover mine, right? And Gilmore, you actually raised two really excellent points. The first point I want to echo what you mentioned about actually a lot of our work actually really sort of like inspired by this whole idea about can we democratize this high quality kind of like healthcare access, right? So I'll give you one example, right? So some of you might have heard me talking about it last time, right? So, but think about sort of like cancer and really standard of care still fail a lot of time, right? So, and then clinical trial often is the last hope. But what's actually really sad and depressing is that oftentimes patient couldn't find trial, right? The matching trial, and then the trial couldn't find enough patient. So here are some really sobering statistics in the US, right? So less than 3% of cancer patients actually enroll in trial. On the other hand, 40% of trial failure is because simply they couldn't find enough patient in time, right? So, and to some extent, that's actually, and there are actually real world examples. I have a colleague who learned about our work, and then she shared some of her real life example where her brother was diagnosed with late stage leukemia in East Washington state, right, which is kind of like community hospital. 85% of cancer patients are actually treated in community hospital in the US, right, even for one of the richest country in the world. And that hospital actually do sequencing, and so it's not like just a very kind of like backwater kind of hospital, right? But unfortunately, the mutation revealed that her brother actually have a mutation that renders standard of care doesn't. So the prognosis would be 6 months, right? So my colleague persuaded him to literally just drive 2 hours to the west, right, to Seattle, to Fred Hutch. That's one of the big NCI designated cancer center in US. And there, the doctor actually find that his profile is actually a perfect match to just a newly coming out trial, right? And his leukemia is on remission, right? So that's actually something that feel inherently super wrong, right? To your point, right? So but that's actually we are already have 80/20 technology to fix, because basically all it takes is that on one hand, each trial has actually a lot of the elaborate, inclusion and exclusion criteria, right? Eligibility criteria, and they are specified in natural language. But LLM actually, like GPT-4 out of the box, can already parse very complex matching logic there. The bigger bottleneck is actually like cancer patients tend to, could have up to hundreds of pages, right? And document notes, right? And a lot of the key information for the matching actually buried inside those. Sometimes you need to synthesize multiple notes. However, so right now, the state of the art, the baseline is that you have those trial coordinators, right? And each one looking at a single cancer patient may take 2 or 3 hours, right? And in the US alone, every year, 2 million new cancer patients, right? So that doesn't scale at all, right? But LLM can actually already do 80/20 job, right? To pass through those notes to actually figure out those important information and then do the matching. And in the past, so here the paradigm shift is that in the past, I'm an NLP person, right? So traditionally, we know how to do, even with first generation foundation model, right? Let's take a BERT model, right? And then let's fine tune with a few example. Okay, solve one task. Unfortunately, there is a problem that Chris Ray at Stanford, right, called the death by 1,000 cut problem, right? So there, in order to do the clinical trial matching, you may have to do 200 tasks, right? So each task, yes, is solvable, right, by very bright grad students and so forth. But unfortunately, when you have hundreds and hundreds of those tasks, right, then it becomes harder and harder to actually do it. The good thing about sort of like this kind of like frontier models, right, is that they start to having, once they see enough of the public web, once they get in large enough, they have this emerging capability to start actually doing all those hundreds of tasks without actually a lot of prior training, right? Without any specialized prior training, and few short example in context learning, it can actually already do 80-20, right? We also find that sometimes you can even treat this kind of model as a very smart assistant. You can ask them to read the freaking manual to do stuff, right? So like, for example, like AJCC staging criteria for cancer is very elaborate, right? But what we find is that we can cram that into a prompt and then literally ask GPT-4 to say, look, like here's a summary of the notes, here's a prompt, determine what's a clinical staging for me, right? And determine what's a resist, stage for me, and so forth. And so what's kind of like, back to your point, Guillermo, is that we have, for example, developed, like, it's not even a whole lot of resourcing, right? So I have a small team, but we actually work with Providence, which is one of the big health system in the West Coast in the US. And now our clinical trial matching system, actually they start using daily in their tumor board, in some of their high profile trial. And the technology, I would say 80-20 is already. What's actually left, right, is actually 99% of the hard work, which is social engineering, right? Which is how can we build the infrastructure? How can we, gain public trust and also respect like privacy, compliance, and so forth. But I would say the technology already sort of like changing the possible kind of like, ROI, so that yesterday this is completely infeasible because no hospital can afford to hire 10,000 trial coordinator, right? But the LLM to some extent can empower those human experts to do 10x, 100x, 1,000x, right? So now suddenly you have a giant army of trial coordinator, virtual trial coordinator to do it. So I think that's a really, really exciting feature that, exactly as you point out. And then in terms of sort of like the growth area, I would say that if you look at a lot of the underpinning technology, right, underpin the transformer and so forth, and underpinning the GPT for trainings and so forth, all of them are invented in academic, right? So self-attention, self-supervision, like gazillion way to do self-supervision, for example, right? Like dynos and so forth. They are all based on ideas that invented in academia. Flashy attention, right? Actually, we all love and use OpenAI, all love and use. That's invented at Stanford, right? State space model. I just love Chris Ray's team's work, and that's invented in Stanford. That's becoming a very interesting alternative to transformer, right? Like members and so forth. So I would say that's actually on one side, right? That's actually to some extent, like, for example, when we work on AI, we tend to think about human-computer symbiosis. I think there is also amazing academic industry symbiosis here, right? I will also say that if I look at the frontier model today, right, on text, actually they are doing amazingly well, even for biomedical context, right? So partially the reason is that the internet have 30 million PubMed papers, right? Have gazillion WebMD pages or podcasts or what have you. So this frontier model already consume all that, right? So biomedical concept, they are already very familiar in the text modality. However, once you go beyond the text, once you go to the multimodal, many of these frontier model actually become super blind and couldn't hear or something, right? So we have actually evaluated something on like even just a table stick, right? Like 2D chest rate, even that kind of very simple task, right? And the frontier model, actually, none of them work very well. So I would say, like, I mean, you did a lot of excellent work on the sensors and imagings and so forth. I think in those domains, when you look at the public web, there is not a whole lot of multimodal longitudinal data out there. So how could frontier model, right? There is no free lunch in machine learning and AI, right? So I think that's another great area where actually there is lots of innovation waiting to be discovered. So.
Thanks, Hoifung, for that. Guillermo, is there anything you want to add, kind of as a final kind of statement on that, or as a brief response, just as I think we're getting towards the end of the session now?
I think that we are all on agreement. I was very excited to hear about the cancer. Let me just add the last component that for the audience to know. The last time, this was a couple of years ago, I was in a presentation about a person that developed multiple of the cancer drugs available in the market, and she shared that all the way to shipping a cancer drug is about $4 billion. Cost, and she said that's nothing. We'll recover that on the first year of the use of the drug. The problem is all the drugs that fail after 2 billions or 3 billions. So the one that spent 4 billion has to recover not 4, has to recover maybe $20 billion for all the failures on the way. And she said it would be awesome if machine learning makes you fail after 1 million, 10 million, even 100 million. It would be great. Because today that's the expense. Drugs, part of the reason they're expensive is because they need to recover the money of all the failures.
And Guillermo, if I may jump, this is where, again, the academics more than anybody else, our own group, for instance, is doing a lot of cutting edge research on machine learning to change every single piece of a clinical trial.
Exactly.
And we have done a tremendous amount of work in the last couple of years to deal with these nasty problems. It's a
partnership. Each one has its goal, and each one is best as one thing or another. I want to really thank you for giving us the opportunity to be in front of all of you. As Mihaela knows, I'm always welcome. Time difference, I love this because most of my time I spend very late days working with the West Coast. I have so much fun when I get requests from Europe because my mornings are very available. Happy to come anytime.
We will keep that in mind, Guillermo. We will keep that in mind.
Anytime.
Thank you so much, Hoifung and Guillermo.
Thank you.
Thanks so much.
Thank you so much. I want to echo that as well. And we're always very, very happy to have you. So I think the pleasure is all ours, both Guillermo and Hoifung. So thank you so much for joining us. Just before we lose everyone, wrap up, I just want to share a couple of brief things. The first is that if any of today has inspired you, maybe you've not started your PhD yet, we're still, as a lab, recruiting for PhD positions in topics including large language models. You can find more details on our website if you're interested and want to apply, but please do so as soon as possible if you've not done so already. And then just finally, today's session will be on YouTube soon if you missed anything or want to share with any friends or colleagues. And our next session will be also on large language models, but of a very different flavor and exploring very different applications of large language models. So please do join us for that on the 11th of March. Finally, just a final thanks again to all of our speakers and our 2 panelists and for everybody joining. Thank you very much and goodbye.